Okay, so let's have a look at improper fractions, at partial fractions and the process and the role that they play in integration. If we remember that, I guess the definition up here, if the degree of the top function, g of x, is less than the degree of the bottom function, it's already a proper fraction. So then we can go sort of straight into our partial fraction process. If it's equal to or the same, well, then you might need to do a division first, all right? So for those that are already proper fractions, it's all about the nature of the denominator. If our denominator is easily factorizable, if that's a word, we can split them up into linear factors. Well, then it will break up into a over x plus a plus b over x plus c sort of thing. So as two linear factors, all right? So I think from memory, over x squared minus 2x is x minus 3 x plus 1 dx, which is the form that we've got here on the right. So that means we can split 9x plus 1 into the form x minus 3 x plus 1 is equal to a over x minus 3 plus b over x plus 1. Now we're going to approach it this way first. I guess the first thing we look at is the denominator, the derivative of the denominator present in the top. So 2x minus 1, is it in the top? No, it's not. Okay, there's no factor of it in the numerator. We could then possibly split that function up as 9x over plus 1 over f of x. We've done that in the past. But again, that 2x plus 1 doesn't help us in terms of the 9x term. And we could certainly, for the second part, complete the square on the denominator, then look to use a tan function. But it's because the 9x term is proving an issue, we might look at factorising that denominator and see where that leads us. So obviously then, I'm going to leave a little bit of space here. We get 9x plus 1 is equal to a outside of x plus 1 plus b outside of x minus 3. If I put x equal to negative 1, I get negative 9 plus 1 is equal to negative 4b. So b is equal to negative 8 on negative 4, which is 2. If I put x equal to 3, I get 28 is equal to 4a. And we get a is equal to 7. So then my integral can be written as a 7 over x minus 3 plus b 2 over x plus 1 dx. So now, hopefully, we're looking at that thinking, the derivative of each of the denominators is 1. It's pretty much present in the top. So we can write each of those separate antiderivatives as 7 natural log of x minus 3 plus 2 natural log of x plus 1 plus some constant c, which is probably enough. We could write it as natural log of x minus 3 to the power of 7 times x plus 1 to the power of 2. Let's have a look at 2. If we have a repeated linear factor, now we're going to have the same issues if that was expanded. X squared minus 4x, 2x minus 4 is the derivative. It's not going to be a factor of the numerator. So let's look to use our partial fractions, which would be of the form given here on the right. So we can say over x minus 2 squared is equal to a over the linear factor repeated plus b over, what if I'll do it the same way we've got it up there. So it's just repeated in the one place, yeah? So if I cross multiply, I'm going to get 3x plus 1 is equal to, I get a over, so we'll do long process, x minus 2 all over x minus 2 squared, x minus 2. So then if we sort of cancel common terms on everything, whoop, 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 I do end up with, so if you like, the 3x minus 1 over 3x plus 1 over x minus 2 all squared is equal to a x minus 2 plus b over x minus 2 squared. So if we just equate the numerators, 3x plus 1 is equal to a outside of x minus 2 plus b. So now if I put x equal to 2, I'm going to get 7 is equal to 0 plus b. B is equal to 7, and now I can put any value for x that I like. Might just put x equal to 3 to keep everything positive. I get 10 is equal to 3 minus 2, which is 1, a plus 7. Therefore, a is equal to 3. So my integral is given by a over 3 over x minus 2 plus 7 over x minus 2 squared dx. So now I've got an integral there that I can actually antidifferentiate. So to make life a little bit easier, we can just write it as, well, hopefully I realise that here's my log expression again. And let's write this one as x minus 2 to the negative 2 dx, because that's going to be my linear expression raised to a power. So my derivatives, first term, 3 natural log, the absolute value of x minus 2, plus, okay, so what is it? We add 1 to the power, so I've got 7 x minus 2, we add 1 to the power negative 1, divide by the new power, divide by the derivative of the bracket, which is 1, plus c, so I get 3 natural log of x minus 2. I'm going to make that a minus 7x minus 2 to the negative 1. So let's just go with 3 natural log x minus 2 minus 7 over plus some c.